forward. I know I've been talking a while, but I want to just now spend just some brief time talking about the different FTIR spectroscopy types. Will just be very brief, okay? So the first one, transmission, I would wager that none of you are aware of this technique because this is old school. I'll say school. But this is how I learned how to do FTIR as an undergrad. Okay, so salt optics work best for IR because they are IR transparent. So when we look at these nice, fine, pristine optics, those are actually sodium chloride solid. And I love this figure here. You can see if we start with just some crystalline sodium chloride, and we add a lot of pressure and a lot of money because it takes time to do these and quality control, then you end up with this beautiful transparent disc. Now, sodium chloride is okay. KBr is best. And that's due to the hygroscopicity. So sodium chloride takes on water. That's what hygroscopicity means. It'll take on atmospheric water. And once these things take on water or any other material that it is soluble in, your optic is ruined. So you can see this person cleaning this optic. Typically, they use a long chain alcohol. Isopropanol is usually okay. But these salts will not be nearly as soluble in the longer chain alcohols as they will be in water. If you were putting water on your salt optic like that, you'd be totally screwed. But KBr is far less hygroscopic than NaCl, and it gives you nice, lovely looking optics. And I use KBr exclusively in my lab when I can. Let's do it like this. Sorry, I'm going to change my little qualitative. We'll say this is okay, this is good, and the piece de la resistance, zinc selenide. That's the jam. Zinc selenide makes lovely salt optics, and it is chemically resistant to everything. So you could expose this stuff to ozone. You could expose it to fluorine radicals. You could expose it to UV light, and it will not degrade. Okay? It is also extremely expensive, even more expensive than our salt optics here. And it's very brittle and easy to break. And I'll share a story with you. In grad school when I was doing some transmission FTIR with zinc selenide optics, I broke 3 $500 zinc selenide optics in one day. So anytime that you break a beaker, anytime that you've damaged something, I guarantee you haven't broken $1,500 worth of salt optics in one single day. Okay, so here's what happens with these salt optics and why we use different techniques now. So pressing these things, or even when they become damaged from atmospheric water, or even sodium chloride is suspect to being oxidized. When it gets oxidized, it'll release chlorine. So you can see how an IR spectra, a transmission IR spectra, right, will become quite crappy as your salt plate degrades. Okay, so that's why zinc selenide is the best for transmission. But you guys didn't do any of this because we don't have a transmission accessory. And what I want to point out, right, all FTIRs are the same. They're all the same garden variety instrument that uses the Michelson interferometer. What makes various types of IR special are the accessory. Okay, so this is a transmission accessory. It's just a little device that can hold 2 sandwiched optics. So that's the lingo, that's the terms we would use. So this would be your analyte, right? A little drop of your analyte right there. And you would sandwich it between two optics, much like you were preparing a cover slip for microscopy, right? And you put it in this little accessory that holds those two plates together, and you pass a beam right through it. And so, as you also might imagine, this is not quantitative at all because you have no idea what the path length is. Okay? So this is the type that we have at HSU Chemistry. Okay? That FTIR that you used up in the OChem lab is actually called an attenuated total reflectance. It's called an ATR. It's still a garden variety FTIR, but it takes advantage of total internal reflection. Okay? And recall, we described this earlier. Total internal reflection occurs when you're at, right, this magic angle that allows a beam to pass right through. And typically it's passing through your optic. So this is your, ATR crystal, but that's your optic. And that could be a salt optic. That could totally be a piece of sodium chloride, potassium bromide, or zinc selenide is the best. Okay? So this is called a multi-bounce ATR crystal. This is the type that we have. We have a single bounce. And now if you can picture that IR up in the OChem lab, right? You spike your sample right down in that little cup, and you put the press over it, okay? And the IR beam actually comes up from underneath through this crystal. The one that we have at HSU is actually a diamond, believe it or not. So that's even better than zinc selenide because it's not going to get damaged. Crazy expensive, okay? As you might imagine, it's a diamond. And also, you don't expect it, but diamonds are IR transparent because carbon is not going to interact with an IR beam, right? A pure carbon lattice, there's no dipole moments, there's no asymmetrical stretching. So an IR beam will pass right through it, okay? Which is pretty cool. And so you just get a single bounce off of this. So, and it does just fine for your detection. And again, not quantitative, okay? Very difficult to be quantitative with this technique. And the main difficulty of being quantitative with IR is just because the path length. You have no clue what this path length is. Same with the ATR. And now the multi-bounce is for really low concentrations or even for molecular level detection. So for example, there's lots of cool studies out there where people have taken these ATR crystals, oops, I'm going to draw like a parallelogram, and they actually bind molecules to the surface of these things. I'm just going to show like generic molecules being bound here. So people will actually do some surface chemistry on their ATR crystal. They'll actually chemically bond some molecules to that ATR crystal. So one singular molecular layer. And if you get enough bounces out of your ATR crystal, you can actually detect that single molecular layer of molecules with this ATR technique. So it might not be quantitative, but it's extremely sensitive. Okay? And so the final technique that I'll describe, and I know, like I said, I've been talking for a while, so I hope this is interesting for you. So this is what I take advantage of in my own lab, which is called drifts. And I love this acronym. So as I like to tell people, if your technique has a cool acronym, that means you're doing something hip and modern. So drifts stands for Diffuse Reflectance Infrared Fourier Transform Spectroscopy. And once again, this is just garden variety, regular old FTIR, but it's the accessory that makes it special. So this is our drifts accessory. Okay? And so it's just this complicated little device that gets placed in the sample compartment of an FTIR spectrometer. And so again, recalling our photophysics, diffuse reflectance, right, is when we have non-specular reflectance, right? So we have a rough surface, and as each beam of light comes in, it scatters off of the surface normal, okay? And you can see that that's being highlighted here. So drifts is used for powder solids, and powder solids only, because if you have a smooth surface, if you have a smooth solid that you've put in there, you're going to get predominantly specular reflectance, okay? Which could also be a technique, but that defeats the point of doing diffuse reflectance, right? So diffuse reflectance is for powder solids, okay? And so you can see a powder solid like this, right, will have lots of spaces in between. And so the light gets scattered around in all different directions, including even into the solid. And so because of this, what happens is you have a very small, what's called sample depth. In other words, the IR beams that scatter back off the surface and eventually make it to the detector. So again, you can see it's a very convoluted set of optics. And it is no easy task aligning these optics to get the light to come in, bounce, scatter off the surface, and make it to your detector. This is not a fun job. Luckily, my students did it for me. So that's a good rite of passage to do spectroscopy, to align the optics of something like this, okay? So, and you can see actually this elliptical mirror, you can see it right here. There's the elliptical mirror, okay, which is pretty cool. And so that elliptical mirror will close over this sample holder. So this little device you're seeing right here is our solid sample holder, okay? And so our sample depth is typically only about 1 micrometer. And so what that means is the IR beam that's scattering off the surface that eventually makes it to the detector is only coming off the first micron or so of the sample. So that makes this a surface sensitive technique. Similarly, ATR, the ATR technique I just described, that can also be used for surface science as well, as I described. If you do some very careful chemistry on your actual ATR crystal, that can be done for even smaller than 1 micron, right? You can detect molecular layers with the ATR technique, okay? And so now this technique is most useful if you want to, for one, investigate powder solids, but two, where this technique really has a lot of use is in doing action spectroscopy, okay?